Okay. 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 So we're talking about a review of what amounts to pre-calculus. Are there any questions? Any questions?
No.
No? Oh, good. We're trying to review pre-calculus in a manner that it would reveal what is and what is not important. And what is important is anything linear will have to reappear, and everything that is not will not. Okay, so that's why as the topic indicates, it is about relations, and fortunately the only relations that we care about right now are linear relations, and that's the good news right there. The linear relation with two variables is nothing but a line. Okay, so that's the general relation is what you are, that equation that you can see right here. Okay, so no matter what A, B, and C are, with one exception, is a straight line on the plane, including all vertical lines. And as such, it creates a relation between x and y, but it is not necessarily a function. And the point here being is that we want to, relations come before functions. Okay, because every function is a relation, but not every relation is a function. Okay, so as you can see, sometimes it's possible to turn this relation into x in terms of y, or y in terms of x, and that creates a function, but generally we don't know. We'll put that aside for the time being. There is one more observation to be made for the near future. It is, in fact, it is a relation between x and y. Another interpretation of this, it is the left-hand side is a linear function of xy. That's what a linear function of two variables is. That's the what's on the left. Okay. So once again, say ax plus by is the only, in fact, a linear function of xy. Okay, so in other words, x and y are the two variables, and they appear in a linear manner. What does linear manner mean? It means that simply that we multiply those variables by a constant number. So these are the two variables, and be a constant. Okay, so that we'll face also soon, because we're unlike calculus 1, we will not be limited to one variable or one dimension. So that's the very first step towards the multidimensional situation, because then if you think about this is what we have, z is equal to ax plus by, so we already have three variables. Okay, so that will be, we will take it all the way to multiple dimensions input, multiple dimensions output. At this time, we'll just start doing a review, so we're looking only at things that are you saw in calculus 1 or before, and I don't presume that you saw functions of two variables necessarily. Okay, so what we need to review next is a review of the Cartesian system of coordinates. And we're going to do it deliberately, in a kind of deliberate manner, so not jumping to what you do so much in calculus 1, and that's the xy plane. Before the xy plane, what comes before xy plane? What? Well, that's right. So xy plane is two-dimensional, two axes. You'd better start with one axis, y, because, like I said, we're not going to stop here. We are continuing this way. Okay, so this is Calc 1, pretty much limited to this setting. If you want to go on with calculus or with linear algebra, you go into dimension 3 and higher. So it's better to start in the beginning, and the beginning is dimension 1, not 2. Okay, so what is the Cartesian system of dimension 1? That's the question. We want to review it. It's very simple, obviously, but the transitions, these transitions from dimension to the next is actually what's more important than what actually we're looking at. So if we understand how to get from dimension 1 to dimension 2, it will be so much easier to go from 2 to 3, and on and on and on, because, like I said, adding an extra dimension is what we're talking about. So what is the Cartesian system in dimension 1? What is it? It is the number line. That's right, the number line. We and then so the axis, in fact, is the number line, and then you move on to xy plane. Well, the x-axis is still the number line, and then we have a copy of the same number line for the y-axis. So this is x-axis, xy, x, y, and z. So axis is a number line, and what does it mean exactly? It means that there are certain features that a line has in addition to, well, being just a line. So if you remember Euclidean geometry, it is you have a piece of paper, draw a line, that's a line. What makes a line a number line is, well, first of all, this one, probably a good idea to start with the direction indicating where the positive direction is, and the other one that becomes negative. What else? So direction. What else? What?
The numbers.
Right, yes, but if we really want to, how about one number to begin with, which is what? 0. Right, so it's better to start with only one number. Okay, and then we there's what's the second most important number? 1. Okay, so the good thing about it is that it gives you a measuring stick, so you can measure that in the direction to the left and to the right, and you have at least the integers have been covered. Then you have all the markings on your line that are like this in both directions to begin with. And then if you care, and we do care, is we also want to introduce fractional numbers and ultimately the real numbers, and that's why the full name is the real number line. So we don't want to skip any. It's not an line of integers. It is a line of real numbers, and real numbers are points on that line, and vice versa. So every point is represented. So every real number has a single representation on the line, and vice versa. Every point on the line will have a single representation as a real number. So that's the idea of the real number line, as well as the one-dimensional Cartesian system. There are certainly subtle points there. It is what to do with all those real numbers, and in fact, you cannot entirely avoid calculus here in order to figure out what is the meaning of pi is and why it is here somewhere, what is that meaning is. But let's just assume that it is given to us once and for all, the real number line with the markings all over the place indicating any number. So if we have a number, we can find a spot on the x-axis for it, and vice versa. If you have mark a spot somewhere on the line, you will be able to find a real number to represent it. Okay. Okay. So that's the connection between geometry and algebra, also known as analytic geometry. And now we take this understanding into the next dimension, dimension 2. That is, we have then 2 copies of a real number line. No problem. we should skip real. 2 copies, and one for x and y. Is there any difference between them? There isn't, but on the other hand, it doesn't have to. It doesn't mean that they have to match in some particular way. So we should be able to see something like this, for example. We for the time being at least, we ignore the units. But the point, but it's still there is a this is no more than a visualization. So if our x-axis has markings close to each other, then the y-axis doesn't mean anything really, because like I said, it is a visualization of a coordinate plane, and then that's what it is. And the meaning of the coordinate plane is pretty much the same as the number line, except instead of one number, you'll have 2. That's all. Okay, so as that sentence that I have on the left, the sentence I have on the left here is repeated, except, like I said, instead of 1 real number, I'll have 2. So let me repeat it nonetheless. So every pair of real numbers has a single representation on the plane and vice versa. Okay? So 2 numbers, 1, 2, you'll have a point with coordinates 1, 2. So about that in a minute, but probably makes sense that that is an operation that goes both ways, from a pair of numbers, nothing but that, and then a point, which is actually, you can draw it on the plane. Where is that point? So 1, 2 here. Hold on a second. 1, 2 over here. That might point P. Okay, but you should realize that we are in the same exact, we are repeating the same procedure as in 1 dimension. So given a real number, we find its location. How do we find that location in that manner? Either we use the markings, or we use the markings initially, and then we use subdivision to find the smaller, like where is 1/2? Well, halfway between 0 and 1, and so on. Okay, so let's assume that this is we understand this part. We understand perfectly how to find a real number representation for every point. No, let's go backwards. For every how to find real number representation for every point, as well as for every point. For every real number, find its point on the line. Suppose we know how to do this. So suppose we know how to do this. We use this information in order to learn how to do that 2-dimensional thing. So pair of numbers, we split it, right? And then we carry out this operation on left for separate for x and y. So find x equal 1 on the x-axis, as well as find y equal 2 on the y-axis. Okay, so to begin with, so that's literally our understanding of the coordinate system in dimension 1 comes into play here. So this is what I'm doing. So this is 1 over here. I found that point 1, and I found the point 2 here. Okay, so well, certainly not the end of the story. So what's next?
Intersection.
Of intersection of what? No. Lines. Yeah. So we draw a vertical line through the first point, right? So that's the beginning over here. Step 1. Step 2. Lines parallel to the axis, to the other axis, as a matter of fact. So this will be parallel to the y-axis, right? and this one will be parallel to the x-axis. And then indeed we take that step number 3 is the intersection. We know enough of geometry here to conclude that two lines that happen to be perpendicular to each other. That's how we chose our x's to be perpendicular. So if we have two lines perpendicular to each other, they will have one intersection. So that's why the result is unambiguous. So that's my point P over here. Okay. So that's a three-step procedure, and then but once again, remember that there are two parts in our statement over here. The one that we're looking at in the middle. Two-part statements. We did the one pair of numbers give me a point, which I did, backwards from point to two numbers. You reverse the, I suppose you can say you reverse the steps. So you suppose we have now P, and we are going backwards. So we don't have anything but a point P over here. And we're supposed to find its representation, so what do we do? Draw parallel lines parallel to the axes, like this, through our point. And then what? And then find the intersections with the axes, and those will give me my coordinates. So this is the x coordinate of P, and this is the y coordinate of P. So in this particular case, suppose I have maybe like this. So it turns out the discovery of through this geometric construction, we discovered that P has coordinates that appears to be 3 and 5. Okay, so it goes backwards. Okay, so that works out fine. I did not mention it, but it's certainly worthwhile to remember that our x's in the Cartesian system are chosen to be perpendicular to each other, and that's why it makes things simpler, but that's not going to be forever. So it is possible to choose Cartesian system that to begin with might have a different angle between them. Okay, so that certainly is a possibility. That part of what we study in linear algebra. Okay, so once again, this is a review. Let's at least have a peek into higher dimensions with the same plan. Let's at least try to have an idea of what we would do with in the same manner in dimension 3. So the way we did it, how we got dimension 2, we used the dimension 1 twice. Okay, so one idea, and certainly the picture suggests that you use the dimension 1 3 times. It is dimension 3, there are 3 x's, and we use them. And we can certainly do that, but, well, we certainly do, and we do it. But in addition, what else do we do? What else do we see in our three-dimensional Cartesian system on the right? We see 3 x's, what else?
Origin.
We see the origin, yes, but what else? In addition to the lines, what do we see? Well, I didn't draw it, but we see planes. The planes is a big deal, right? Because we have spent all this work and time figuring out the dimension 2. We could just as well should use that information to build up to the next level. So then, if we know how to do it, well, that will be helpful. So anyway, they are planes, and those are called the Cartesian planes, right? So the Cartesian plane will be the xy plane. There will be yz and xz planes. So it's like walls in the corner of the room. There's the floor, and there are two walls meeting together. So these are the Cartesian planes. So this is XC plane.
Does it matter what side of the
on which way X is pointing, it doesn't matter. In calculus might not as much, but it will matter. So what matters is, in fact, is the order of the axes and which way we're turning from X. So the order is the same, X, Y, Z, obviously, the order of the axes. But if we move X pointing in the opposite direction, then that trip will be as we move from X to Y. Remember the right-hand rule, anyone? Right-hand rule. You turn, or a screwdriver, or whatever. There are other names for it. So you imagine that you have a screwdriver and you're turning from X to Y. You're supposed to go in the Z direction. Okay? So look at it once again. So I'm turning from X to Y like this, and my thumb, that's the right-hand rule. So even if you're lefty, you have to use the right hand. So you turn from X to Y, and then this is the Z-axis. So that's just to make sure that it is indeed, you see that it makes a difference. So imagine that I have my X and Y axis, Y and Z axis are the same, but I move X over here, which is sometimes you see that. Now if I'm turning from X to Y, my fingers will be from X to Y, turning from X to Y, and then my thumb will be pointing down, so opposite direction of Z. This is called orientation. Orientation, so it matters, but only in the geometric sense. So if we actually have a specific idea, a specific space we're living in, and we want to orient ourselves in a particular way within that space, then it does matter. However, if you think about the algebra, then you realize that it is how do we represent a point in three-dimensional space? It's a triple. So all points will be that's the idea that we're getting from this ascension of dimensions, is that there will be every point in three-dimensional space will be represented by a triple of numbers, as well as every triple of numbers can find a point in the space, as long as X and Y and Z are chosen ahead of time. Okay, so that's the idea of the Cartesian system. Usually we stick with one system at a time, but we will have to, in this course in particular, we'll have to look into the possibility of different systems and how to translate from one to the next. In dimension one, even in dimension one, you can imagine that what if I point my direction in the opposite direction? What if I move 0? If we're talking about the actual space, then there is no origin anywhere, and there are no units. Or if there are units, we can switch from, say, inches to centimeters, and we should be able to pretty much translate the whole body of science, of knowledge, into and it should still work, right? So imagine that we have all the physics or everything else written up, and then we choose the units. So what is happening to the body of knowledge? It should still be valid, and that how we translate one to the next is usually question.
Yeah, are there an infinite number of dimensions?
Are
they going to keep counting on?
Yeah, definitely. Yes,
Okay.
yes, absolutely. So 1, 2, 3. We're not going to stop. It doesn't have that there are infinite many of them, but it doesn't mean that we're going to be studying infinite dimensional spaces.
Okay.
So all the spaces we'll be looking at will be finite dimensional, but there's no limit to the dimension.
Okay.
If it makes sense.
Yeah, it does.
Right. So infinite dimensional spaces are also interesting, but we're not going to be doing those. So dimensions are growing, and so why do we study dimensions beyond 3? Anyone? Yep. You don't have to raise your hand if you just.
Because we live in a three-dimensional universe, so we have a tough time expressing how a dimension beyond 3 would work.
Well, you were answering why we need. I think what you were explaining is why we need algebra in order to understand high dimensional spaces. that is the purpose of this class, and will not be able to understand higher dimensions without algebra. The class is called linear algebra, and so the algebra is ultimately how we understand dimensions that we cannot, or quantities or phenomena that we cannot visualize. So beyond dimension 3, we cannot visualize things because we are living in three-dimensional space. So yes, so that's the purpose of the class. But still, why do we study 4 or 500 dimensional spaces?
Because something in a lower dimension can exist in a higher dimension.
Right. Yes. That's certainly a possibility. Yeah.
Is it because our like concepts and ideas, like maybe a piece of software could operate in like a data structure that's
Okay.
5-dimensional or something like that?
How many dimensional?
Well, 5-dimensional.
How about 100-dimensional? What's stopping you to have 100-dimensional data structure?
I mean, just the limits of the computer, really, isn't it?
No, I don't think it's really a problem. You just so 2-dimensional will be a table, and then 3-dimensional is a cube of numbers. But if you have to visualize it, but it's really no problem to go to dimension 4 or 100. It depends on how many. Instead of thinking databases, how about something more practical? Prices. Each price might be changing independently. So suppose let's take prices. So let's take stocks. 10,000 stocks traded on the stock exchange. Okay, every one has a price. So you have right away you have 10,000 numbers. Okay, each of them is changing independently. So if you have 3 prices only, 3 stocks, that picture on the right will be sufficient. Okay, so the motion of the stock market will be then simply motion through the 3-dimensional space. At every point, you have 3 numbers. At every moment of time, you have a point in 3-dimensional space, and those 3 numbers give you the price of those 3 stocks. If you have 10,000 stocks, then what? There are 10,000 at every moment of time. There are 10,000 numbers, and you what? You're moving through the 10,000 dimensional space.
So it's more,
What?
it's kind of like giving you more storage in a way, I guess you could say.
It's
So if you had $20,000, you'd have 20,000. Or 20,000 stock, you'd have 20,000 dimensions.
Yes.
Right.
Yeah.
Okay.
Yes, because like I said, everyone is a number, and it might be, at least you can assume that one of them is changing independently. So it's like 10,000 degrees of freedom, and that creates a 10,000 dimensional space. Right? So there are only, if you look at the plane, you can move independently only vertically or horizontally. So there are only 2 degrees of independent degrees of freedom.
Yeah.
Okay, so for example, if you put a spring on it this way and that way, it will be oscillating in any kind of way you can imagine. So there are only 2 degrees of freedom. However, if you're dealing with a man-made phenomena or anything else, you will end up with as many numbers as you make up, and then properly think about it would be to create an appropriate dimensional space for it, for the data to live in it. So it could be stocks, could be prices, or anything else. How about experimental data? So maybe you are measuring 100 things. You were doing a scientific experiment, and you're measuring 100 things independently, and then you write down 100 numbers. And once you carry out 1,000 experimentation, you'll have 1,000 strings of 100 of numbers of 100 entries. Okay, so then you'll have 100 dimensional space, because as far as you know, you have 100 quantities that you're measuring, and then they might be changing dependently, maybe independently. You don't know yet. But to begin with, you will say that this is a 100 dimensional space. Okay, and then impossible to visualize, right? So that's why we'll stick to lower dimensions in order to get some kind of intuition or about how things work in dimensions in general. when everything is linear, and then hope that we can translate that understanding into higher dimensions. But ultimately, it's algebra. But the course is called algebra. Every time we can, we will visualize the things that we can, but ultimately, everything is resolved with algebra. Okay, so you can imagine now what happens then as we proceed with this idea. Then this part disappears, right? So this, what I was just talking about, is how you can represent triples of numbers in the three-dimensional space, but it only works because we are living in this three-dimensional space to begin with. So this point over here in the space has coordinates if we have chosen our coordinate axis. So for example, you take that corner as the z-axis, this is the x-axis, and over there it is the y-axis. Okay, so once they have chosen, then and units are chosen, any point I pick here will give me, can be found, coordinates for it can be found. Okay, so, well, but then what happens if you go even to dimension 4? And, if you go to physics, there's even in physics, they're talking about physical space, and yet they need high dimensions sometimes just to understand things. It just takes space-time, four-dimensional right away. So visualization fails, and the algebra comes in, so that part about representations disappears, and we will be talking pretty much about nothing but strings of numbers. So let me do this out here. So any string of real numbers is a point in the string of n real numbers. So we have to make sure that the number 6 is a point in the n-dimensional Cartesian space, Cartesian or Euclidean space. Okay, and vice versa. So I repeated the same sentence as what we just discussed, except it's just not working as well anymore because there is no n-dimensional space for us to look at and gain some understanding about the algebra and about those strings. Okay, so then what becomes this sentence there, which seems to be a statement about what we can do, which is reality. It is in fact more of a definition. So. What is an n-dimensional Cartesian space? It is simply this, all the strings of n numbers. Yes.
Just a question real quick.
Yeah.
What's the word before Cartesian?
Dimensional, n-dimensional. So this is how I would put it. So the n-dimensional Cartesian space is the set of all strings of n real numbers. No picture, because it's n-dimensional. You can try to imagine what one-dimensional, two-dimensional, three-dimensional. I mean, you see that the three-dimensional already fails because we're trying to make a picture of something three-dimensional limited to the two-dimensional piece of paper. Okay, so I don't know. So it gets worse every time. Every time we add an extra axis, it gets worse, and we can't really visualize it anymore. Well, at least you can see how what happens is in a different kind of manner. So if you start with 1, and then you add an extra dimension. Okay, so once again, this is my x-axis. I add the y-axis in the perpendicular direction. So here I have my x and y axes, and I add the z-axis in the perpendicular direction. So now imagine we have 3 axes. Add the 4th one in the perpendicular direction. Can you? So 3 directions, X, Y, and Z perpendicular to each other. Add the fourth, also perpendicular. Which way?
Would it be going up as well?
What?
Would it be going up as well?
Well, then they're not perpendicular to Z. It's parallel to Z. No, there is no answer because there is no room for the fourth axis in the three-dimensional space. So that's in part what linear algebra studies is if the space is three-dimensional, what does it mean exactly? Well, you can have three axes parallel, perpendicular to each other, but not four. Okay, so that makes it three-dimensional. Okay. Okay, so that the definition will have to be certainly explained many, many times before we become comfortable with it, and primarily is being illustrated with low dimensional pictures. Okay, so that is the Cartesian. So this is three-dimensional thing. I'm trying to add one more dimension, but where does it go? And there is no place for it. Okay. Dimension 1, dimension 2. Okay, so a little bit more about functions and relations. I think that's what comes next. No, there is one more. Since we're talking about this, this is what n-dimensional space is. There is an attribute of the spaces, and there are two main ways to do anything meaningful in these spaces, dimension 1, 2, 3, or higher. And one is doing vectors. Okay, so we'll get to that later. So in other words, algebra. So that's the linear algebra. There is one thing that you've seen elsewhere in Calculus 1, and that is you can measure things. Okay, so you can use the coordinates in order to measure things in this space. Does it ring a bell? How do you use coordinates? Well, let's say coordinates of 2 points in order to find the distance between them. No?
There's the distance formula.
That's what I'm talking about. We use coordinates to calculate instead of measure distances. So if we have a Cartesian system, then every point on that line, plane, or higher dimensional space is supplied with its coordinates. Okay, so every point has those two numbers. So it's like everything has been mapped. So every point on a certain area has a coordinate attached to it, and it is helpful because now we don't have to measure. We can just do a calculation. And once again, I don't want to do jump to dimension 2. How about we start still with dimension 1? So point P, point Q, what's the distance between P and Q in terms of their coordinates? Almost. Also good. Which one? Absolute value, right. So it's Q minus P absolute value, which is the same as P minus Q absolute value. Okay, so that's the distance. The distance between P and Q is done with the absolute value. And once again, here I'm using P and Q simultaneously to indicate to stand for points, names of points, as well as their coordinates, which are numbers. So you take those 2 points, their coordinates are numbers, subtract those 2 numbers, take the absolute value, you have the distance. As you can see, so you don't have to do any measuring whatsoever. All we have to do is those numbers. In dimension 2, indeed, the answer is the distance formula, but let's be clear, this is also the distance formula. It's just one dimension. Okay, so I have point P here with, say, coordinates AB, and I have point there with coordinates CD, right? And then, once again, the distance is frequently denoted by dPq, distance between P and Q, whatever that dimension is. So what's the distance formula? Oh, somebody mentioned distance formula. So what is it? Right. Well, yeah. So in other words, well, maybe let's not jump to it. Let's just follow the same idea that one-dimensional computations are being recycled in order to produce computation for higher dimensions. So if I already know the distance formula for dimension 1 on left, now I want to produce the distance formula for dimension on right. So what do? I'm looking at the coordinates, right? I'm looking at the coordinates for, this is A and B. So the point P is A and B, and the second one is has coordinates P and Q. I'm sorry, C and D. So this is C, and this is D. Okay. What we're after is this distance, this one. Okay. So how do we go about finding it? Using geometry. What am I talking about? The Pythagorean theorem. Okay, so this is the triangle, probably right triangle that have my segment between the 2 points as my hypotenuse. So, and then I'm using all I needed to apply the Pythagorean theorem now is those two sides. So the horizontal side, this one is what? What is this? According to what we have on the left, the distance between C and A. C minus A, right? C minus A, absolute value. Okay, so that we use literally the distance formula for dimension 1 applied to the x-axis. I do now distance formula for dimension 1, but applied to the y-axis. So I'm looking at, what am I looking at? I'm looking at this part over here. Running out of colors here. This one. What is this one? The green one? B minus D, absolute value. Okay, so we have two sides, and the Pythagorean theorem gives me the square root of, what is it? C minus A, absolute value squared, plus B minus D, absolute value squared. And usually absolute value drop because it's squared anyway. So that's the distance formula. A little bit of time left. So dimension 3. You can conjecture what the answer is. 3 coordinates. No, actually, compare the formula for 1 dimension, 2 dimension. It seems like they're different, but really look at it. So anybody wants to guess what the 3-dimensional distance formula is? There will be the third term. Right, so it's still square root. Why? It is still above the Pythagorean theorem. So we will we'll do it later, but it's, the idea is that you're not looking at a rectangle as I'm looking over here. This is a rectangle, right? And we found it's diagonal. We know the size of the rectangle found is diagonal by the Pythagorean theorem. So in dimension 3, it will be a box, and we're still looking for its diagonal. We find it in 2 consecutive applications of the Pythagorean theorem, and so it will be square root plus the third term. Okay, so it will be the same. Okay, so we'll resume this next time. Try the web work, and I'll see you on Friday.